Welcome back to the fourth section of Chapter 3. In this section, we're going to be looking at something called linear programming. Now, this isn't like computer programming or anything like that. It's really just one step beyond what it was that we did last time, which was solving systems of inequalities. And so we're going to be doing a lot of systems of inequalities, and then it's just a little bit more. So our learning target for today, I can solve linear programming problems. So linear programming, what it is we're going to be maximizing or minimizing some function called an objective function onto a set of constraints. And so let's look to see what that is. We'll start out with a set of constraints. It's just a system of inequalities. A lot of times we'll have these guys, x is greater than or equal to 0, y is greater than or equal to 0, because these will be real world type problems, like things that actually happen. And we usually don't have negative things that happen. And so we'll have these. Sometimes it'll be x is greater than or equal to 2, because maybe we have to have at least 2 of whatever these are. Right now we don't have any kind of context with this. We're just going to look at a problem by itself. So for this, we need to graph it. So we have our graph. We're going to graph x is greater than or equal to 0. So that's going to be a vertical line, and we want greater than or equal to. Y is greater than or equal to 0. So that's a horizontal line, greater than or equal to. And so we're looking at just the first quadrant. And that's going to be true in most cases. So you really only need to graph the first quadrant generally. Now y is less than or equal to 3x plus 3. We can start at 3. We'll go up 3 over 1, up 3 over 1, and get our line. And we want less than or equal to, so let's plug in a point. The origin's not on that line. Is 0 less than 3? Yes, it is. So we can shade the side with the origin. And then y equals negative x plus 7. So we can go up to 7, down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. Get that line, plug in the origin again. Is 0 less than 7? Yep. So we shade that side. And so the overlap of all these is this area right in here. It's going to be inside this little shape. And this, last time, we called this the solution region, because this is where all the solutions are. For linear programming, it's the exact same thing. We call it the feasible region, because this is where the solutions would be feasible. It's our possibilities. And this is a bounded region because it's completely closed in. An unbounded region would be, say, this greenish one right here, where it just keeps going off into infinity. So bounded means it's entirely closed in. Unbounded means that it could keep going. Most of what we'll be working with are bounded, but not necessarily. And so then those were our constraints. We graphed our constraints. Now we have another function, maximize p equals 10x plus 16y for the constraints. These were the constraints. And this function is called our objective function. So we're trying to maximize or minimize. And so we just need to plug in all the points in here to see which is going to be the biggest. That seems pretty easy enough. I mean, we only have an infinite number of points in this region. And so, well, maybe plugging in an infinite number of points isn't going to be the easiest thing in the world. Luckily, we have what's called the vertex principle of linear programming. Try and say that one a few times quickly. So it's a mouthful. But what this vertex principle of linear programming says is that if an objective function has a maximum or minimum, it has to occur at one or more of the vertices of the feasible region. Vertices would be plural for vertex, just like mooses is plural for moose. So the vertex would be where it has an angle. So the vertices are just all of these corners. So what this principle did is it narrowed down the infinite number of possible solutions that we had to plug in to only 4. I like those odds a lot better. So we just need to plug in 4 points and see which one makes the biggest. And we're going to do that. And so, by the way, in a bounded region, the objective function will have a maximum and a minimum. In an unbounded region, an objective function will have a maximum or a minimum. And the other one, it could just keep going. So, have to go to another page, but we have our constraints. The objective function is going to be important. The graph, only have the piece of the graph that's actually important right now. And then we need to figure out what these vertices are. Well, this one's 0, 0. That one's a pretty easy one to figure out. And then also this one's a y-intercept of the function, so that's just going to be 0, 3. This one down here is the y-intercept of this, or the x-intercept. So when y equals 0, what would x equal? X will equal 7. So we have 7, 0. Now we just have to figure out this one. It looks like it's 1, 6, but we can set these two equal to each other to find out. So we have 3x plus 3 equals negative x plus 7. We can add the x over and subtract the 3 to get 4x equals 4. Divide by 4 to get x equals 1. Then if we plug 1 in, negative 1 plus 7 is 6. 3 times 1 plus 3 is 6. So we have the point 1, 6. Now we just need to plug these 4 points into this one. So, easiest way of doing that is a table. We'll have our points 0, 0, 0, 3, 1, 6, and 7, 0. And then we'll have the equation, and then it equals the actual value, the p-value. I put those in 2 separate columns. And so we can plug 0, 0 into the equation. 10 times 0 plus 16 times 0. Well, that's going to equal 0. Plug in 0, 3. 10 times 0 plus 16 times 3. Well, that's 0. 16 times 3 is 48. We can plug in 1, 6. 10 times 1 is 10. 16 times 6 is 96. 10 plus 96 is 106. And plug in 7 zeros. 10 times 7 is 70. And that's 0, so we have 70. And so we're maximizing. Well, 106 is the biggest. So it's going. The maximum will be at 106. The maximum is 106, and it happens at this point. A lot of times, it will be asking for one of the 2 pieces. It might be asking, what is the maximum? That would be 106. Where does the maximum happen? 1, 6. If it doesn't ask or you're not sure, you can always say the maximum is blank at blank. If we were trying to minimize this, by the way, every step would be the same except we'd look for the smaller number. Look for 0. So that's how linear programming works. Now let's look at a linear programming problem, because real life doesn't throw a system of equations at us. Real life throws a problem at us, and then we have to then make it a system of equations. So here we have a dentistry problem. It says Dr. Lee's dentist practice is open for 7 hours each day. His receptionist schedules appointments, allowing half an hour for a cleaning and 1 hour to fill a cavity. He charges $40 for a cleaning and $95 for a filling. Dr. Lee cannot do more than 40 fillings per day. Find the number of each type of appointment that maximizes Dr. Lee's income for the day. That's something he would want to do. He'd want to maximize his income each day. And so we have a lot of information here. Let's pick out some information and start making some inequalities. First piece of information people generally pick out: 7 hours each day and half an hour for cleaning, 1 hour for filling. And so we have time that we're looking at here. We can make a time inequality. Well, half an hour for cleaning, 1 hour to fill a cavity, and it's only can be up to 7. So this would be half an hour times number of cleanings plus 1 hour times the number of fillings. Then it has to be less than or equal to 7, because we could work for less than 7 hours, but he can't work for more than 7 hours. Is it possible that he worked for 0 hours in a day? It is possible. That would be a really slow day. There are no appointments. Does he want to do that? No, because he's not actually making any money for doing that. So we have 1/2 C plus 1F is less than or equal to 7. Next piece of information. Oh, he has $40 for cleaning and $90 for filling. So that would be 40C plus 95F. But what does that equal? We don't have another price in there for price equation or inequality. But look down at the last sentence. What are we trying to maximize? Find a number and type of each appointment that maximizes Dr. Lee's income for the day. This would be his income. This is the objective function. So we don't need it to equal something. It's going to equal P. Why is it going to equal P? I don't know why they chose P, but that's generally what it is. You could have I if you want, but P equals the 40 times cleaning plus 95 times the filling. And so if we add those together, we'll see how much he made for the day. All right, we need some more inequalities. This one inequality isn't going to be enough. We're not going to have overlapping areas. Well, what else do we have? He cannot do more than 4 fillings. So the number of fillings has to be less than or equal to 4. So F has to be less than or equal to 4. And that's really all the information that it gives us. We only have 2 inequalities, which could technically be enough, but if we want a bounded region, we're going to want some more. There are some more in there, it just doesn't tell it to us. For instance, what is the least number of fillings that Dr. Lee can do in a day? I know personally today I have performed 0 cavity fillings. I haven't done a single one all day. That's my minimum. Teeth cleaning, yes, I have cleaned teeth, not professionally, but I have done some amateur teeth cleaning today. So the fillings has to be greater than or equal to 0. And same thing with cleanings has to be greater than or equal to 0. You're not going to clean negative teeth. And so, and notice I mentioned that, hey, we're probably going to have those happen. And so we can graph it. We only really need the first quadrant. And then important here, we need to label stuff. Here, I use C and F for cleanings and fillings. That's fine. Need to label, hey, my x-axis is going to be cleanings, my y-axis is going to be fillings. If you don't, somewhere in there, it almost always gets flipped around. The other option would be to use x and y, but we would want to label x as the number of cleanings and y as the number of fillings. So we do need to attach those at some point, either here and keep it as C and F, or define what x and y are. Then we can graph. I'm not going to graph the greater than 0 ones. I did that by choosing this graph. So we can still graph the other ones though. We have F is less than or equal to 4. So fillings, he has to do less than 4, so we have a line at 4, and then it has to be less than that. And then here, I would use intercepts. If C equals 0, we have 7. And if F equals 0, C would be 14. So we can go from 7 to 14, connect the line. Notice I don't have arrows here because it can't go negative in either way. So it's really just connecting the 2 points here. And then less than that, 0, 0 works because, yes, he could do 0 cavities, 0 fillings. That will most likely not be his maximum, though. And so we have this area here is the overlapping area. This is our feasible region. So we just need to pick our vertices and then plug them in. So We have C comma F. We have, well, the origin. That's an easy one. And then we have 0, 4, which was, it's the y-intercept here. Then we have the other y-intercept, which we found when we were graphing it. That was 14. So we have 14 comma 0. And now we just need the intersection point. Well, we know that one of them is f equals 4. So just plug it in. You can subtract to get 3. So 1/2 c equals 3. So c would equal 6. So we have 6 comma 4. Now we can plug them in. Plug in 0, 0. Well, we're going to get 0. If you don't work, you don't get paid. Plug in 0, 4. 40 times 0 is 0. 95 times 4 is 380. Plug in 14, 0. So 40 times 14 plus 95 times 0. 40 times 14 is 560. So I'd rather do all cleanings than all fillings. But how about the fillings and cleanings? So plug in 6, 4. 40 times 6 is 240. 4 times 95 was 380. We already saw that. Then 240 plus 380 is 620. So which one maximizes? The 620. And so now we need to make sure we answer the question. Is it asking for what is the maximum that Dr. Lee can make? Or is it asking for what does he have to do to get there? Find the number of each type of appointment that maximizes. So each type of appointment, we have 6 cleanings and 4 fillings. So 6 cleanings and 4 fillings will maximize his income for the day. So this is linear programming. Notice it's not like programming a computer, but what it is we have our constraints, we graph them to find our feasible region, and then we plug the vertices into an objective function, which will, then we look for our maximums and minimums. So that's this topic. Make sure you do what you have to do after this, and I will see you next time. Until then, happy mathing.